Okay, so it's my pleasure to be hosting today Falk Feddersen, who's a professor at Scripps Institute of Oceanography in San Diego in the US. Falk has been in San Diego for a while. He did his PhD there in 1999, and he's part of a handful of experts, gurus on surf zone dynamics. He's a specialist in nonlinear wave dynamics in the surf zone. He's also done a lot of research on nearshore circulation and inner shelf dynamics. So he's a hardcore physical oceanographer, dynamicist, and he does both experimental, and he's combining his experimental work with also numerical work, and he's also done a lot of theoretical work on breaking waves and nearshore dynamics. Yeah, so I'm hosting him for his sabbatical for a few months here, and yeah, honored to have you here, and excited to listen to your talk on the effect of wind on depth limited overturning wave shape.
All right, thank you, Mark. All right, it's a pleasure and an honor to be here at the Max Planck Institute giving this seminar. So I'm going to tell you guys today about some recent work that me and a number of colleagues have done, basically trying to quantify the effect of wind on overturning wave shape. And I'll define all of this coming up. And this talk is going to be in two parts. The first part is we're going to look at field scale observations. Now, typically when we say field scale, we mean in the ocean. But in this case, the field scale is in a laboratory facility called the Surf Ranch that makes waves that are actually big enough to surf and big enough to, this sort of like realistic scale. And these are all the colleagues that were involved in this piece of work. And then we're going to transition into doing some numerical modeling of situations relatively analogous to what we did at the Surf Ranch. And these are some of the colleagues that we have for this aspect of the work. Here are the affiliations, and then lastly, this work was funded by the Mark Wolfinger Surf Zone Processes Research Fund. This is not sort of like funded by the National Science Foundation or Office of Naval Research, the typical sort of agencies that are thing. This is a family foundation, very much interested in the science of the surf and the science of surfing. And so, it's pretty cool. Okay, so before we get started, what I wanted to do is sort of like discuss a little bit of philosophy first. And so this is famous portrait of Alexander von Humboldt. And you guys all know who Alexander von Humboldt is. In the States, they don't all know who Alexander von Humboldt is. But sort of like a scientific hero to many people, including to me. And one of the things that he'd like to go out there and actually get into the thing, right? And one of the quotes that sort of resonates with me is that nature must be experienced through feeling. And what I get in that is that, hey, if you want to study waves, you need to actually get into the waves. If you want to study the mountaintop, you better climb the mountain, these sorts of things. And so I think this is something that is really important to consider and to remember in our day and age today where, and I am exactly the same, we just sit at the computer all day, craning our necks, trying to kiss the screen. Okay, but this here is important. The other scientific hero, and you guys all know who this is Walter Munk. I'm sure he spent a lot of time here over the years with his association with Klaus Hasselmann. And Walter Munk, fortunately, was at Scripps, and I got to spend a fair amount of time with him. And one of the things that he consistently said from the first time that I really talked to him as a graduate student is that we need to listen to the wisdom of folks like mariners, sailors, divers, and surfers, because they know things about the ocean that we as physical oceanographers, again, sitting in our offices, sitting at our desk, don't know. And they can tell us things about the ocean. They may not know the mathematics, they may not know the physics or something like that, but they can tell us something about the processes that we can then use as hypotheses to test. And so, like, to me, these two things, these two sort of like quotes go together. Okay, so what are we going to investigate? Well, here is a photo of a wave at the Surf Ranch under what we call offshore wind conditions. And offshore wind means that the wind is blowing into the face of the wave like this. And you see there's a very nice overturn. A surfer could probably fit inside that barrel. And here is the same case, but for onshore wind. And with onshore wind, you can see the wave size is more or less the same, but you can see this overturn here is quite a bit smaller. Be hard for a person to fit in there. Maybe a tiny child could fit into that overturn. And why would we even want to fit inside that overturn? Because surfers love to be inside these spaces. It's called getting barreled or getting tubed, right? And that's sort of like the ultimate thing in surfing. So you notice there's a difference in the size of these two. There's a difference in the size of these two overturns. Well, surfers know that. They know that when the wind is offshore, it's going to be good for surfing, and when the wind is onshore, it's not. Okay? So first we have to talk about how we classify wave overturns. And so the traditional way is there's a classification where you have spilling wave breaking. And spilling wave breaking is when you see wave breaking like this, where, you know, it's kind of hard to say there's actually an overturn. There's just a little bit of perhaps an overturn, but nothing really very dramatic. Then Galvin, who did this in 1968, you can classify waves also as plunging. And here's a very beautiful example of a plunging wave at a spot in Hawaii. And you can see that the lip throws all the way out and is going to connect again on the bottom of the wave, where here the lip connects right at the very top of the wave. And so there's fundamental difference in these two things, but the problem with this is that the classification system is qualitative. I could look and say, yeah, that's a spilling wave and that's a plunging wave, but then what about in between, you know? Okay, well, why is this important? The way that a wave breaks affects how turbulence is injected into the water column. How turbulence is injected into the water column then will affect how sand gets lifted up and gets moved around. Okay, so this isn't only something that is fun for surfers, let's say. It's important in other types of arenas. Okay, so let me just give you an example. Here is a relatively recent article from JGR Earth Surface. Field observations of turbulence, sand suspension, and cross-shore transport under spilling and plunging breaker waves. And one of their key points, this is nice, AGU makes us do these key points now, suspended sediment loads and onshore transport rates were larger for plunging than for spilling breakers. That's pretty interesting. So like the quantitatively sediment transport is different under spilling than for plunging breakers. Not actually a surprise, perhaps, but it's interesting that it's quantified. Now, but there's a problem. What they did is they had an observer with a clock looking at the waves breaking on their instrument and said, spilling, plunging, spilling, plunging, 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 spilling. That's a little qualitative, right? So I'm not doubting these results, but sort of like the methodology is very qualitative. And there's lots of other papers that do sort of like the same sort of thing. Okay, so one can quantify wave overturns, and some of these folks here, Blenkinsop and Chaplin and O'Day et al. 2021 have done this. This is a figure from a Blenkinsop and Chaplin paper where they have a photograph of a wave overturn behind this little grid, and then they draw this figure here to indicate the shape of the overturn at the moment where the lip of the jet impacts the water surface. And from that, you can get a width and, you can get a width of the overturn, and you can get a length of the overturn. Okay? And Michael Long-Higgins, who's a very, very famous fluid dynamics applied mathematician, particularly when it comes to waves, had done some work on this sort of thing, and he came up with this very useful functional form. I'm not going to show you the functional form, but this blue outline indicates the functional form of the overturn, and you can say, all right, there's this length here and a width here, and Blenkinsop and Chaplin used that functional form to fit to fit their data and get the lengths and the widths. And the key things is that you get an area, which is kind of like the length times the width, and an aspect ratio, which is the width divided by the length. This has also been recently done by Annika O'Day and colleagues, 2021, where this is at the Field Research Facility in Duck, North Carolina. And this is the crab, and they mounted a lidar on right there. on the crab in these kinds of breaking waves, and they visualized the wave overturning. And they got data that looked like this. The gray dots are the lidar returns, and you can see this overturning wave, the overturning wave shape. And then they fit that overturn, that's the blue curve, and they get a length and a width. And from like this, you can quantify the shape of the overturn. Okay, so what affects an overturn? Well, one thing that's known to affect the overturn is the bathymetry that the waves are propagating and shoaling over, right? In particular, the wave slope. So here are some figures from Stefan Grillet's 1997 paper, where they use a boundary element model where they're solving Laplace's equation in the interior of the fluid identically, and then matching the surface and the surface kinematic and dynamic boundary condition. And here they tried a bottom slope of 1 in 100, and you can see they have this initial soliton propagates up a slope and it overturns, and you can see the size of the overturn here. And then they try a 1 in 35 slope with the same exact initial condition, and you can see how much bigger the overturn is. Okay. You can also do something similar in DNS models. You can have a relatively low slope and a relatively high slope, and you can see the difference in the overturns. This is from a paper by Wouter Mostert and Luc Dijke, JFM in 2020 using basilisk. Okay. There's something about this though. Surfers already knew all this. Every surfer knows that when you have steep bathymetry, it's much better for creating large overturns and the likelihood that you're going to get too. And because the value function for surfers is, can I fit inside the overturn? They like the steep spots. Now they're also more advanced as well, so beginners shouldn't be chasing them. Okay, so here we have Walter and his quote: "Listen to the wisdom of mariners, sailors, divers, and surfers." Surfers know that offshore wind leads to larger overturns, but this has not previously been sort of scientifically studied. Okay, and so here's those two photos again. So setting up that hypothesis. What's nice about this facility now is I told you the bathymetry can change the shape of the overturns. The bathymetry here is the same, and the wave that's generated is nearly identical. It's a laboratory. Now there's some small variations, but nearly identical. So that the idea now is that the differences between those two cases is really then just a function of the variable that's changed, which is the wind. Okay. Why is it important? Because it affects turbulence and sediment transport. Surfers have long understood that offshore wind leads to larger, more square overturns. And there have been some previous studies on the effects of wind on wave shape. There have been these papers that have studied how wind affects where in the cross shore the wave breaks, so the breakpoint location. Me and Fabrice Veron, we did something where for shoaling waves, how the wind affected the shoaling waves. And then there have been some other papers as well, some much more theoretical. Okay, up to now, no controlled field scale observations. Okay, so surf ranch experiments, 12th to the 14th March. Here is an aerial photo of the surf ranch. It is about 600 meters long in that direction and about 50 meters wide in that direction. It's a big lab. What happens is a tram pulls, well, I'll show you guys that later. We had a met station for wind that we mounted about 16 meters above the water surface. We have a photogrammetry drone flying over the waves, and then we had a wave staff. And here is this rig here that had a wave staff on it, and we mounted a Velodyne lidar on top of this rig. That was mounted in the center of the basin right here. And what happens is the waves get generated and they basically pass by the rig and slam into it. There's the lidar out there looking down on the waves. And what happens is that this tram pulls a foil underwater, and in this case, it's propagating in the plus Y direction. And the black dot is the location of the rig, and it's in not deep water, it's in constant water depth here, propagates up a slope and then in a flat region, and that's where the waves break. We have a coordinate system where X is the cross tank coordinate, Y is the long tank coordinate, and 0, 0 is at the location of the rig. That's the rig. Okay, so just to orient you, here is a video of what it looks like. Here is another drone that we were flying. Here is the rig with the lidar. Here is the tram that has a foil underneath it. And out to hit the rig. Boom. So that's pretty fun. Okay, so now we also have cameras on each end of the wave basin that are constantly filming this. This is a system that the company puts in because it's a paying facility for surfers, and all surfers want to watch themselves. Well, see how they surfed afterwards. Okay, so here is this for offshore wind, and we call this a right wave because a surfer surfing on it sees open face to the right. We call this a left wave because a surfer surfing on it sees open face to the left. And you can see the waves hitting the rig, and you can see the difference in qualitatively the difference in the overturn size between one and the other. There's also other things, like you can see the spray coming off the lip of the jet as it's coming, as the offshore wind just rips the spray off, where you don't see that kind of effect here. Okay. So here is an overview of what these two waves look like. So again, these are still shots from that camera system, and this is the magenta diamond. I'm sorry, represents the location of what we call the breakpoint. So this is where the lip is impacting the water surface. Okay. These panels here, as a function of time, so it's a little bit more than 6 seconds here, is data from the wave staff. So for this wave, the wave came up, it peaked a little bit over 2 meters, and then slowly came down. And for this one, the wave came up with a little bit less than 2 meters and came down. And so that's the data from the wave staff on the rig. And then here, these are just some snapshots of what the lidar data looks like. So the rig is located here. It's shooting multiple beams out like this, and the colors, the dots represent the lidar returns, and the color represents the elevation. So blue is lower, and colored is higher. So you can see we're visual, and we're setting that on top of this georectified image from the drone. So you can see the drone and the lidar are seeing the same thing. Okay, again, the bathymetry is fixed, and in total, we have 22 waves that are very similar. And there are 11 left waves and 11 right waves. Again, this is a right wave and that's a left wave. Okay, so now from the georectified images, we can estimate the breakpoint location. So for each image, and these are images taken at 5 Hertz, we can estimate where the lip is impacting visually. And to be honest, this was just done by hand. And the X's represent that location. And then for all the images, and the red dots represent for the images shown. Okay. The next thing is we can also then rotate ourselves into a coordinate system where X tilde is in the direction of wave propagation, and Y tilde is in the along wave crest direction. And so that's X tilde, Y tilde, and from now on we'll be going in this X tilde, Y tilde coordinate system. The wave speed is at 6.7 meters per second. And then what we do is we rotate the wind into a wave coordinate system. So we measure the wind, and then we rotate it into this coordinate system, and we take the component in the X tilde direction, and we divide it by the wave speed. So UW on C is our non-dimensional thing that says how strong the wind is. Offshore wind is going to be less than 0. Onshore wind is going to be greater than 0. We don't boost into a coordinate system that shows the window, and we'll talk about that later. Okay, so now let's take a look at some lidar observations. So here we have the same image as before, and now I'm showing this arrow here that sort of represents what the view would be like if you were looking straight into the overturn. And if you're looking straight into the overturn, you would see something like this. And here's a nice photo of a gentleman named Felipe Toledo, who's a 2-time world champion. That's sort of like the view that you would get, and that's sort of like where the surfers want to be. Okay. So if we now say, all right, cool, we're going to take a look at that view, we're going to basically have data that looks like this. So now here we have 2 waves, a left wave here and a right wave here, all as a function of x tilde, so the direction of wave propagation, and this axis here is z. And what we're doing is we're stepping through time from this one to this one to this one. So you can see the wave is here between -7 and -8, here it's between -5 and -6, and here it's between -3 and -4. So as the wave is propagating and getting closer and closer to the lidar, you can see it moving through space. And so this here is now a left wave, and this here is now a right wave. And you can see we're imaging a lot more of the right wave than or more features of the right wave than of the left wave. Okay, so now how do we use these lidar observations to quantify wave overturning? So again, we have a view into the wave like this, and what we do is we take a number of 2 meter wide slices, 2 meter wide slices in the y tilde direction. So data that's just be, let's say, in this box, and that represents this panel here. So here we're kind of out onto the wave face, and at the very moment that the wave is just starting to, the lift is starting to form, or the jet is starting to form. And then we keep going to the next panel, that's 2 meters over, 2 meters over, 2 meters over, 2 meters over, 2 meters over. And if we were to say this location here, oh, and these are overlapping slices, I should have said that, is that this is here, so you can see that, like, for the most part, the wave has broken, okay? And at this moment here, the lip has not connected, but at this moment, the lip has connected. So we take this to be our time and y tilde slice representing the wave overturn. All right, and so now, again, we use this functional form developed by Long and Higgins and have been used by these other folks, and we fit to a region containing the overturn. And so here is the data that I showed you from that previous panel. The dots represent all the lidar returns in that 2 meter wide swath, and the black dots represent the points that were used for the fit. And you can see the fit to that shape looks really good, and we get a length and a width. Okay, and again, this is kind of like that part of the wave right there. I didn't do that. That one's hard to see. Okay, so now let's take a look at a number of different waves. So we have 2 left waves here and 2 right waves here and this is showing now all the data. And then the black dots represent the locations that are used for the fit, and the crosses represent the length and the width that are inferred from that fit. And so you can see there's variation in this overturn shape, left waves and between the 2 right waves. Okay, so now we're going to test some hypotheses. We're going to examine wind effects on wave shape. And so the wave parameters are the breakpoint location divided by the surf zone width, the non-dimensional overturn area, and the aspect ratio. And we're going to compare this against the non-dimensional wind speed. Okay, and the hypotheses are that for offshore wind, this is going to be closer to shore. For onshore wind, further from shore. For offshore wind, we have larger area. For onshore wind, smaller area, and similar for the aspect ratio. Okay, so first let's take a look at the breakpoint location. So here we have the breakpoint location, non-dimensional breakpoint location here, versus the non-dimensional wind speed. And remember, plus is onshore wind, minus is offshore wind. And so what we're seeing is that for offshore wind, the wave is breaking closer to the shore. And for onshore wind, it's breaking farther away from shore. This is actually consistent with previous laboratory studies that were waves that were like this big. Okay, so now we can take a look at the non-dimensional overturn area and the aspect ratio. And so here we see for the non-dimensional area that when you get onshore winds, the overturn area decreases very rapidly. And then for offshore winds, it sort of hangs around 0.4, sort of like looks like it equilibrates there. And for the aspect ratio, there's a pretty consistent functional variation with the aspect ratio with the wind. Again, consistent with surfers' experience and demonstrating that the wind has a strong effect on overturning wave shape. Should note that the difference in the area can go from 0.4 down to 0.2, And the aspect ratio can go from 0.5 down to like 0.25. So it's pretty strong variations in these parameters, and just little variations. Okay, surfers already knew this, but like this is good because, well, I mean, we're using Walter's methodology basically to develop hypotheses into for testing. Now, one thing that's important is that these effects are not incorporated into wave models that are used in sort of like coastal engineering practice or even nearshore processes science, Boussinesq type wave models or coast couple swan and roms, these sorts of things. Okay. Mechanism? Well, we can take inspiration from deep water wind wave modeling, and there they concluded that pressure forces on the interface are much, much greater than viscous forces on the interface. And these are just two examples here. There's some other papers that have also concluded this. And I just like this photo of offshore wind with this wave breaking here. Okay, so now let's talk about some limitations. First thing, the ocean is usually not fetch limited. If you have, so we made the same exact wave and blew two different wind and had variations in the wind. In the ocean, as soon as the wind is blowing onshore, wind waves are being generated and those will turn into chop and stuff. So you won't have the wave field in the actual ocean changes substantially as soon as you have onshore wind. And if you have onshore wind and then it switches to offshore wind, the wave field will also start changing substantially. So those sorts of processes in sort of like realistic situations can also are also going to affect how waves break. The other thing is that this is one laboratory configuration. We have one bathymetry. We haven't tried a number of different bathymetries. So the relative importance of wind, the incident waves, or the bathymetry in general is not known. We just sort of demonstrated that the wind can have a substantial effect. Okay, so offshore wind leads to more intense wave dissipation, onshore wind, the opposite. And these things will have changes in sediment transport patterns, resulting in perhaps different types of beach morphologies. This work was published in the Journal of Fluid Mechanics, 2023. And now the question is, well, what about more sophisticated models? And for that, you need to have a model that can do multi-phase flow, wind and water. And so now we're going to transition into two-phase modeling of shoaling, a shoaling soliton under wind using basilisk. And so here is a schematic of our model domain. It's similar, analogous to that used by Mostert and Dike in their paper. And for bathymetry, of an offshore flat region here, where there's an initial condition of a soliton that is then released. There's a slope here that is similar to the slope at the surf ranch when you project the slope into the direction of soliton propagation, and then just a flat water region here. The bottom is a no-slip boundary condition, and there's no slip walls on this side and on this side. And then at above C equals 0, up to Z on H naught of 10, there's an inlet here, and there's an outlet on the other side. And this is for wind that blows to the right. And at the very top, there's a slip upper boundary. So there's a ceiling on the lab, but it's a slip ceiling on the lab. Okay. And what I'm showing, and then we have a soliton. What's shown here is the initial condition of the wind, and in particular the vorticity of the wind. Okay, so some of the fixed model parameters that we have, there's the air-water density ratio, air to water density, and the air to water kinematic viscosities. The initial soliton height is 0.6. The initial condition from the soliton is just a higher order soliton solution. And one of the important parameters is the wave Reynolds number, specified by this. We're using 40,000. When you use the actual kinematic viscosity of water in this implies a water depth of 5.5 centimeters, which is small. But these are some of the limitations of numerical modeling. Okay, so some of the model parameters that we're going to vary are the parameter that governs surface tension, that's the bond number, and it's a function of the sigma, which is the surface tension, and we're going to have this at 4,000. And similar to Jiarong Wu's recent JFM paper, we're also going to have a wind Reynolds number, and that is defined in this sort of traditional sort of way, but you can think of the wind Reynolds number as representing the strength of the wind. And we're going to vary this from minus 1,800 up to 2,400. And I'm focusing on the 1,800 and the 2,400 because I'm going to show you guys plots from the extreme winds, and then we'll fill in the regions in between. Okay, another thing that's important, basilisk here is being run in 2D mode, not 3D. Why? Computationally, it's much easier, but also the amount of the data storage is still pretty intense, but once you go to 3D, the data storage is out of control. There's a precursor wind simulation to generate the initial condition that's used here. We're using adaptive mesh refinement with 14 levels of refinement. That's a lot. That means that the minimum resolution here in this non-dimensional coordinate is 0.0037. So that means that we have about 250 or so for every unit. For every unit one over here, you have 250 points. So effectively, it's DNS. Okay, so let's see some videos. Okay, so here we have a case with onshore wind, and you see flow separating off of the soliton as a thing, and you can see the airflow is faster than soliton, but not that much. And then here we have the opposite, the flow is separating off that way, and the qualitatively the flow separation features are quite different. And then there's some problems with the surface tracking. And then this is what it looks like when it's broken. Okay, pretty fun. So now let's go to, let's blow up on it, because when you blow up on it, it's even more fun. So you can see how, the fact that the flow is separating means that there have to be significant pressure gradients along the air water surface. Again, these are just some issues with the surface tracking algorithm. So that's the moment of impact. Now, this is where I stop my analysis because this is what I'm interested in. But if we're to continue on, being in 2D is a little bit of a limitation because now once you're creating turbulence in the water, that's going to cascade down to small scales very quickly. 2D turbulence cannot do that. Okay, so now let's define some geometric parameters related to the moment where the jet impacts. And in scientific parlance, we call it a jet. Surfer parlance, you call it a lip. But yeah. Okay, so this is for the 2400 case. This is for the minus 1800 case. This is the moment of impact. And so we have a couple parameters. This green diamond is the location of the breakpoint. And so you can see here the location of the breakpoint is a little less than 41. Here the location of the breakpoint is more than 42. Now there's a difference there. This here is the highest elevation of the water surface, and that we'll call that the wave height. And so this is also the wave height here. And then we can define the area of the void, of the overturn void, which is demarked by the red dots as that. And then we can also define the area of the jet as this region that's in magenta. And so what I do is I say, I find the furthest location back of the void, go up to the surface, and then bound that area. So you can see this jet here is very clearly seen that the area here and the area there is different. Right? That there's these strong qualitative difference. You can just with your eyes see that there's differences in how these waves are written. Oh, right. And then we could also do the same trick and get the length and the width of the overturn for the aspect. Okay, so now let's see if the breakpoint location is affected by wind speed and direction. So again, remember, this here is the surf range, UW on C, and this here is what the model says. And now this is a function of RA star. Okay, so qualitatively, there's also a relationship. There's also a relationship that looks something like that, although not as quite as elegant as that. the variation, it's largely consistent with what we see at the surf range. Okay, so now we can also look at the overturn area and the aspect ratio. And the surf range is on this side and the model's on this side. So now if we look at the model, here at the surf range, we had sort of like this flat region and then it dropped. And with the model, we have this flat region and then it drops. Qualitatively, it's kind of similar, but here we go from 0.4 to 0.2. Here we go from 0.3 to 0.35 to 0.3. So the variation is not as strong as at the surf range. And then the interesting thing is, this is the aspect ratio, where you can see the aspect ratio decreases for onshore wind. We actually get the opposite relationship, where the aspect ratio increases for onshore wind, as opposed to the other way. And you can kind of see that. This area here, for the offshore wind, this is very oblong, and this is much more circular. But that's counter to what we see at the surf range. So the overturn area, largely consistent with surf range, aspect ratio is not. Okay, we can also then take a look, and this we could not do from the surf range, is take a look at the effect of wind on the overturning jet area. And so again, that's the area of this magenta region. And you can imagine if that's bigger, that's a whole lot of water falling down on your head if you're a surfer, or a piece of sand, a grain of sand underneath the water here. It's going to make a big difference. Again, this thing has pretty strong dependence. So for offshore wind, the jet area is relatively big, over 0.22. And then as it goes to onshore wind, it goes down to 0.13. So it's almost a factor of 2 difference in the jet area between these two cases. This is also consistent with surfer experience, but we couldn't test this with the at the surf range. All right, well, some things are similar, some things are not. So what's the difference? So the first thing we thought of is, well, maybe it's surface tension effects. So we ran some simulations with different bond numbers. And we did bond number of 200 or 1,000. This is basically increasing the surface tension from the previous runs. Just why not? And it's, well, yeah. So we have now some simulations with bond number 200 and bond number of 1,000. And we've overlaid those on these plots of the breakpoint location, the void area, the aspect ratio, and the jet ratio. And to my eye, it's not really any different. The bond number is not causing any of these differences. I'll point out the surf range bond number is 360,000. Maybe we should have gone the other way, but it's harder. I mean, okay. So now I've been doing everything in terms of the wind Reynolds number. So here's this case where we're blowing the wind like that. So what I can do instead is actually estimate the wind speed. And so we estimated non-dimensionally Z on H naught. We were at about 6 of these units, measuring the wind about a height 6 units above the water surface at the surf range. Okay, so here's this dotted line. That's where we were measuring. And so what I can do now is I can take the wind speed and I can average it in time at each location, and I can also average it in X. And so now I get one number at a height of 6. And when I do that, I plot the wind speed here as a function of wind Reynolds number. This looks pretty nice, straight and linear. So varying the Reynolds number varies the wind speed linearly. But now what we see is we're varying the wind speed from 4 down to like almost -3. 4 to -3. So now here's the breakpoint location. And we're going from -1 to -1, a little bit less than -1. If we were to convert this thing here to wind Reynolds number, we're seeing wind Reynolds number variation from, let's say, -800 to 800. Well, if you go from -800 to 800, you don't really see any breakpoint variation. So the model effects are seen at much larger wind speeds than what we actually observe. So I think this will make Mark happy, because like the model is like kind of working, but then it's not working at all. So now the question is why? Okay. So again, Model void area and breakpoint location consistent with observations qualitatively. Aspect ratio is not, but the modeled wind effects occur for stronger wind than observed. So why could this be? Well, a few weeks ago, my wife and I, we were in Cornwall at a town called Penzance, and we saw these tiny little waves under very strong offshore wind conditions coming into shore. And I was just like, that's a soliton that overturns. And the numerical modeling soliton amplitude is about 3 centimeters, and these waves are maybe about that size. And when you just look at that and you see how it breaks, you're like, even though the slope is low and stuff like that, we're just like, that's not really what a wave looks like when you're at the surf ranch, or like a wave that one could actually surf. So the first possibility is the wave Reynolds number is too low. Recall the wave Reynolds number is a function of h to the 3/2. The surf ranch Reynolds number is 14 million. The model wave Reynolds number is 40,000. And it's hard to make that really much bigger, because if you want to be able to resolve viscous effects, you can make it a little bit bigger, but not much. So that's the number one possibility. Okay, number two possibility. Wind turbulence, maybe the wind turbulence is actually 3-dimensional. It's not 2-dimensional. And the problem is in 2D, turbulence cascades to larger scales. So vorticity of the same sign merges to larger and larger scales. Whereas, these things here kind of look like eddies that you see in images of Jupiter or something like that, right? But in 3D turbulence, these things don't do that. They break up into smaller scales. So we've done a simulation at a much lower resolution. And what we're showing here is the soliton coming in, and behind it, projected onto this wall, are features of, let's just say, features representing turbulence. And what they are is, you can see how it's broken down into much, much, much smaller scales relative to these very coherent things that move backwards. Here, in the wake of this wave, there's much less coherent stuff. All right. But does this actually matter for the flow separation and the surface pressure on this guy as it's going? And that's a question I don't know the answer to. Okay. The third possibility, and this is my favorite, is the alongshore length of the overturn. So here we're doing these simulations in 2D. And so what that means is that if you think of it in 3 dimensions, in this direction here, it's extending out to plus or minus infinity. This is a wave coming into shore that extends out to infinity, that overturns exactly at the same time everywhere. You don't see that in real life very often, but you can see something approaching it on the very rarest of conditions. So model overturns extend to infinity. In real life, you see things like this, and this is why surfers like this, is because you can get into the barrel, but you can also get out. You're not, if you were in this tube at this moment in time, the next moment in time, it would close down on your head. So the overturns aren't just extending out to infinity, but they have some sort of conical feature to them, open out here and closing as you go that way, right? And so when you actually get differences in pressure distributions, you get a high pressure that's induced from inside the barrel, and that creates, from high to low pressure, creates a blowing out towards the open wave face. So you see this in surf movies all the time, and so I took a couple screen grabs. This is at this wave in Hawaii. This is former world champion John Florence, and the wave is he's coming out of the barrel here, and at a next time step, you see the spray coming out of the overturn. It's because it's closing so quickly here and it's still somewhat open there. The spray completely engulfs him, and then he comes out. And that spray is generated by the very strong wind velocities or air velocities that are just ripping water particles off the surface of the interior of the face of the wave. So we don't know how strong that wind is, but it has to be strong. And again, we're not including this in our thing. So this is my favorite hypothesis as to, and could this affect basically the aspect ratio of the overturns? Okay, so So the next step is, again, looking at the mechanism, right? So to do that, we can now, I've been showing you all these plots of vorticity because vorticity is pretty and easy to understand. Here now is the pressure field in the air over the soliton. And what you're seeing here for the onshore wind is you see higher pressure here and you see lower pressure over here. And for the offshore wind case where the wind is blowing that way, you see higher pressure here and very low pressure here as the flow is very accelerated, and then low pressure down behind here. This is what you expect, right? Like a car driving driving on the highway experiences high pressure at the front of the car and low pressure on the back of the car. Okay, so what we can do now is we can, and this is just essentially hot off the presses, is we can estimate terms from the surface dynamic boundary condition. And again, this is the equation that has to be satisfied at the free surface, or it has to be satisfied if it's inviscid irrotational with no surface tension at the free surface. And we can estimate this term, and this term. And so how does that work? So in a case, and we're doing this for shoaling for as the wave is still shoaling. So we have the wave profile here for RE star 2400, RE star 1800, and then we can estimate this term, that term, which is the green line, the red term, which is the velocity squared term, and we can also estimate the pressure term. And we do that in both of these. And so the first thing that you notice is that pressure term looks pretty small compared to the other two terms. And when you line those two waves up on top next to each other, you can see there's already subtle differences in how the wave looks at the same exact time. And so now the blue is the pressure distribution for the offshore wind. The red is the pressure distribution for the onshore wind. You can see they're quite different. And here at this point, the air pressure is at about 6 × 10⁻³ The gravity, the G eta term here is also at about 0.6. So it's 100 times smaller. So, or the surface air pressure is essentially at this point 1% of the other terms. So that's certainly not big enough to make a very local sort of change, but could it be big enough to, in a time integrated sense, to make a consistent change? And we don't know the answer to that yet. Lots of people to thank, particularly folks at the Kelly Slater Waves Company and staff, field crews from the SIO and the FRF, Steve Elgar lent us some instruments, Tony DePaolo lent us some instrument, Luke Daike and Jairong Wu at Princeton gave us some really good thoughts and thing. And then lastly, this work would not be possible with the amazing support of the Wolfinger family through the Mark Wald Wolfinger Surfstone Processes Research Fund. The Wolfinger family created this fund to honor their son who had passed away, Marco, who was a very, very avid surfer. So thanks to them. Questions?